So for this set of notes, you need to have your mass spectrophotometer packet and a highlighter. What I'm going to do is point out the relevant information that we're going to use this for. So we've already discussed IR. Mass spec is another tool that scientists can use in figuring out an organic molecule. So we know from IR, we get the functional group. Mass spec is going to be the one that gives us the mass, okay? So it's sometimes called the mass spectrum. And there's a couple different kinds of mass spectrometers. So I'm just going to give you a general overview, but there's many different kinds that you could get. So what I want you to focus on is these set of paragraphs here that kind of describe how this actually works. So if I had a, let's say a cannonball or like a bowling ball versus a tennis ball, and I rolled them down the hallway, and I had a fire hose that could shoot out from the classroom and hit the balls as they were traveling down the hallway. Well, of course, you would see that because the cannonball is so much heavier, it would not deflect much. But if I looked at the tennis ball, and again, they call it a table tennis ball, so it might be a ping pong ball, is of course going to, because it is so light, it's going to have what we call a huge deflection. So this idea of mass of the atom is going to dictate how it behaves in this kind of environment. So let me go through how it's set up and then show you a basic schematic of it. So the first thing that must take place is a thing called ionization, okay? So ionization, again, this should be a Z. I think this is from some English source. So first off, an atom is ionized by knocking off electrons to get a positive ion. So we always have a positive ion in a mass spectrophotometer, okay, even if it doesn't want to be a positive. Then we're going to accelerate it so that we have everybody with the same kinetic energy, okay? So if they have the same kinetic energy, we know that if they get deflected, it's due to their mass, not due to their speed. Then we put it in a magnetic field, okay? And the lighter they are, the more they get deflected, okay? So we could tell by their, how far they go off, and I'll show you a picture of that. And then we have a way to detect electronically, and that is what we get as a mass spectrophotometer. So if you go to the next page, this is kind of a schematic of the inside of a mass spectrometer. So here you put in your sample. Your sample must be in a gas form. You ionize it. Again, you're stripping off an electron. You then accelerate it, and then it will go through the magnetic field, and you will see that if it's lighter, it will get deflected. So depending upon its mass, it will be deflected according to that. And then you have a way to detect it, so on and so forth. So this is all taking place in a vacuum. That's important because if you had other ions in there, it might get deflected because it hits something. So that's very key that it is in a vacuum. Next page. So the ions that we are producing, we're taking off an electron. Most of them are going to be +1, but we will talk about some instances when they are not a +1. But that is what we're focused on. The rest of this you could kind of just kind of read through. But I want to focus on two things on this page. The mass of the ion, the lighter the ions will be deflected more than the heavier ones. And the charge on the ions are deflected more with only a +1 charge. So again, you can have a +2 ion as well. We're not going to focus too much on it. I will kind of mention it a couple places, but we are really going to focus on just the +1 ion. So we can take the mass and divide it by the charge and get what we call the mass to charge ratio. So sometimes you will see it listed as M/Z. That's pretty standard across mass spectrophotometers. So, for example, if an ion had a mass of 28 and it had a charge of +1, its mass to charge would be a 28. But if you had a mass of 56 and the charge is a +2, that would also be a 28. So we are going to stick with things that are just the +1, because otherwise you would have to know if they are +1 or +2. So skipping all the way to what on the top here, it says page 7 of 8. So what does it look like after you run the mass spectrometer? Well, it's called a stick diagram, and literally it looks like a bunch of sticks. This is a mass spectra for molybdenum, okay, the element of molybdenum. So what you will see on the x-axis is your mass to charge ratio, and then on your y-axis is what we call relative abundance, okay? So if I look at this stick diagram, okay, I am literally looking at how many sticks do I have. So if I look at each one of these sticks, okay, I have a total of 7 sticks. So that means I have 7 isotopes, and we talked about isotopes before, of molybdenum. Okay, and this is how scientists figured this all out. We are assuming everything is a +1, by the way, when we're doing this. So if we go down to this little paragraph here, so we have 7 different isotopes, and they all have a mass. Okay, so the number you see underneath them is essentially the mass of that particular isotope. And again, remember, mass is based off of carbon-12 scale, and so that is why these are whole numbers, but you will see how that comes out to be a decimal, like we talked about before. So I will kind of show you the calculations here. All right, so go to the next page, and it has the mass spectra for Borah. Okay, so I could see, this one's a simpler one, I only have 2 sticks. I could see that I have a isotope at 10 AMUs and 11 AMUs. Okay, you have 2 isotopes, because we have 2 sticks, okay? But realize that isotope 11, it's a taller stick than isotope 10. That tells you the relative abundance. But do look that it's 100 versus this one's in the 20s. So how do we equate that? Because when we usually do isotopes, it usually is not, 100 is not one of the options that you have. So what the actual instrument does is kind of equate that to each other. So what we're going to do is find what we call the relative atomic mass. So what you do is, or what the instrument does, is it takes the total. So let's say we total up the 23 and the 100. So 23 of them would be boron 10, and then 100 would be boron 11. Well, what you would do is a weighted average. So you would actually calculate the mass and then divide it by the 123. And that is where you get the atomic mass of boron being around 10.8. So the instrument already does this for you, but do realize that, you know, these sets of notes kind of go through things a little bit more extensively than we're really going to focus on. So if you go to the next page where it says zirconium, okay, and do recognize that there is a little stick there, so you do have to be careful with some of these that you can see what you're supposed to see. So if I look at zirconium, okay, it has 5 isotopes. We'll realize that each one of these isotopes, their masses are listed there, but they all add up to 100%, okay, which is what we saw before. So that's what the instrument kind of does all in one. All right, so one more thing I do want to mention is some of them only have what we call 2 isotopes, and chlorine in particular. This one we're going to come back to. It's a pretty common element to be in an organic molecule. So chlorine 35 versus chlorine 37. Well, realize that you have about 3 times the amount of chlorine 35 as you do 37. So you have a 3 to 2 ratio that you do see. And you would see this on the mass spectra, and that is unique to chlorine. So anytime you see peaks at the end and they are 2 apart and one is 3 times the other, you know that you have chlorine in that molecule. And I'll show you an example of that in another video.